Namaste, everyone, and welcome to The Deep Dive. Today, we're embarking on a really crucial exploration, a deep dive into one of the most fundamental concepts in all of science, thermodynamics. If you're preparing for your Class 11th board exams, or perhaps aiming for competitive exams like JEE or NEET, then this session is absolutely tailored for you. Think of this as your personal guided tour, to mastering the transformations of energy and predicting the fate of chemical reactions. Our mission today is really to demystify this critical unit, making sure you grasp not just the what, but the profound why behind these universal principles. Namaste, tutor. I'm really keen to dive into thermodynamics today. It feels like such a foundational chapter, and I know it's super important for JEE and NEET as well. It just seems so crucial, but, well, sometimes a bit overwhelming. Could we start by truly understanding what this vast field is all about?
Absolutely. Namaste to you, too. You've hit upon a truly powerful subject. Albert Einstein himself once noted, and it's quite a quote, "It is the only physical theory of universal content concerning which I am convinced that, within the framework of the applicability of its basic concepts, it will never be overthrown." That's an extraordinary endorsement, isn't it, from one of history's greatest minds? It really signifies that thermodynamics isn't just, a theory. It embodies core truths about our universe. Today, we're going to systematically unpack the core concepts of thermodynamics. We'll explore how energy transforms, what truly makes a process happen spontaneously, and most importantly, how to quantify these changes for your exams and, well, for a deeper understanding of the world around you. Consider this your essential roadmap to acing this unit step by step. Right, let's begin by setting the stage by understanding precisely what thermodynamics is and, just as importantly, what it isn't. This clarity is vital for your exam success. So at its very heart, thermodynamics is the study of energy transformations. Imagine the familiar gas in your kitchen stove, methane. When it burns, its chemical energy is transformed into heat energy. Or think about how a fuel in an engine can perform mechanical work, or even how a simple dry cell converts chemical energy into electrical energy. These are all diverse forms of energy, constantly interconverting under specific conditions. Thermodynamics is the branch of science that meticulously studies these intricate transformations. Now, a crucial distinction, especially for competitive exams, thermodynamics focuses on macroscopic systems. What does that mean? It means we're dealing with the bulk properties of matter, things like pressure, volume, and temperature, which involve a vast number of molecules, not individual atoms or tiny clusters. We're concerned with the big picture, the average behavior, not the microscopic details. Another vital point is that thermodynamics is concerned primarily with the initial and final states of a system. It doesn't tell us how these energy transformations actually occur, nor does it tell us at what rate they happen. If you're interested in reaction speed, you'll delve into chemical kinetics, which is, well, a completely different field. Thermodynamics merely answers, is this process possible? And what are the overall energy changes from start to finish? The journey doesn't matter, only the destination. Finally, and this is key, the laws of thermodynamics are strictly applicable only when a system is in or moving between equilibrium states. In equilibrium, the macroscopic properties of the system, like temperature or pressure, remain constant over time. Throughout this deep dive, we'll aim to answer fundamental questions using these principles. How do we quantify energy changes in chemical reactions? Will a given process occur on its own, spontaneously? What are the underlying driving forces for a chemical change? And to what extent will a reaction actually proceed towards products?
So if I'm understanding correctly, it's sort of about the before and after of energy and whether something will happen at all rather than how fast it happens.
Precisely. That's a perfect encapsulation of its core focus. You've nailed that crucial distinction. Now, to discuss these changes with accuracy, we need to define some specific terms that form the bedrock of thermodynamic understanding. Let's start with the fundamental pair, system and surroundings. In thermodynamics, our system is that very specific part of the universe where we are intently making our observations or conducting our experiment. For instance, if you're mixing two chemicals in a beaker to initiate a reaction, the contents inside that beaker, the reaction mixture itself, constitute your system. That's your area of focus. Now, the surroundings are literally everything else in the universe outside your defined system. So in our beaker example, the air in the room, the beaker walls themselves, even you, the observer, everything external to the reacting mixture is considered the surroundings. Together, the system and its surroundings make up the universe. It's a simple foundational equation. Universe, system plus surroundings.
Okay, system plus surroundings equals universe. Simple enough.
Right. And for practical purposes, when we talk about surroundings, we usually mean the immediate portion of the universe near the system that can realistically interact with it. And what separates our system from these surroundings, that's the boundary. This boundary can be a physical wall, like the glass of the beaker, or it can be, an imaginary line. Its primary role is to help us track and manage any exchange of matter or energy between the system and its surroundings. Building on that, let's classify systems based on how they interact with their surroundings regarding the exchange of matter and energy. This classification is absolutely vital for understanding how to apply the laws of thermodynamics. First up, we have an open system. As the name suggests, this system can freely exchange both matter and energy with its surroundings. Imagine boiling water in an open pot on the stove. Steam, which is matter, escapes into the air, and heat, energy, radiates out into the kitchen. That's a classic open system. Your own body, for instance, is an open system. You take in food matter and release waste matter, and you exchange heat energy with your environment.
Right, like breathing and eating. Makes sense.
Exactly. Next, we have a closed system. Here, energy can be exchanged between the system and surroundings, but not matter. Picture water boiling in a pressure cooker with its lid tightly sealed. No steam can escape, so matter is contained. However, heat still passes from the stove through the cooker walls to the water inside, and the hot cooker radiates heat back into the kitchen. So energy can transfer, but matter cannot.
Okay, energy, yes. Matter, no. That's closed.
Precisely. Finally, the most isolated type, an isolated system. In this system, there is absolutely no exchange of either energy nor matter with the surroundings. A well-insulated thermos flask with its cap tightly sealed is the closest real-world example we have. The goal is to minimize both heat transfer and matter leakage, effectively isolating the contents. The entire universe, in fact, can be considered an isolated system for thermodynamic purposes, as there's, nothing outside it to exchange with.
This classification seems pretty fundamental. So, is it fair to say the type of boundary really defines the system's behavior then?
You've hit the nail on the head. That's a fantastic insight. Understanding the nature of that boundary, whether it's permeable to matter, energy, both, or neither, is absolutely paramount. It dictates how we analyze the system's energy changes and what predictions we can make. This is a common conceptual question in your board exam, so remember this well. Moving forward, let's talk about the state of the system and state functions. The state of a thermodynamic system is meticulously described by its microscopic properties, the measurable bulk properties like pressure P, volume V, temperature T, and its chemical composition. For any reaction or process, we define these properties both at the beginning, initial state, and at the end, final state of the change. Now, in traditional mechanics, you'd need to know the exact position and velocity of every single particle to describe a system's state. But thankfully, in thermodynamics, especially for chemical systems, it's much more practical. We don't need that level of microscopic detail. Instead, we work with average, measurable properties. Properties like pressure, volume, and temperature are incredibly special. They are called state variables or state functions. The defining characteristic of a state function is that its value depends only on the current state of the system, not on the path or the journey by which that state was achieved.
Oh, okay. So it doesn't matter how you got there, just where you are now.
Exactly. Think of it like this. If you're flying from Delhi to Mumbai, your current location is a state function. It doesn't matter if you flew directly or took a connecting flight via Chennai. Your current position is fixed by where you are right now, not the road you took. Other critical state functions we'll encounter and study in depth include internal energy, U, enthalpy, H, entropy, S, and Gibbs energy, G. We'll dive deep into the latter three very soon. To illustrate, consider a temperature change from 25 degrees to 35 degrees C. The change in temperature, or Etai, is always plus 10 degrees C. It makes no difference if you heated it directly or if you cooled it down to 10 degrees C first and then heated it up. The final change is still plus 10 degrees C. Temperature is a state function. Similarly, the volume of water in a pond is a state function. It only depends on the amount of water currently present, not how it got there. This powerful concept of state functions dramatically simplifies our calculations, allowing us to focus only on the initial and final conditions, which is a huge advantage for problem solving. Now, let's transition into the heart of energy changes within these systems, beginning with a fundamental thermodynamic quantity, internal energy. Internal energy, symbolized as U, represents the total energy contained within a system. When we speak of total energy, we're encompassing all possible forms of energy at the molecular level. This includes the kinetic energy of molecular motion, translational, rotational, vibrational, the potential energy from intermolecular forces, the energy stored in chemical bonds, and even nuclear energy. It's the grand sum of every type of energy present within that system.
So like everything inside.
Pretty much everything energetically relevant within the boundary. The internal energy of a system isn't static. It can change in a few fundamental ways. First, heat Q can flow into or out of the system. If the system absorbs heat, its internal energy increases. If it releases heat, its internal energy decreases. Second, work W can be done on the system or by the system. If work is done on the system, like compressing a gas, its internal energy increases. If the system does work, like an expanding gas pushing a piston, its internal energy decreases. And third, matter can enter or leave the system, directly altering the total energy content. We've already classified systems based on these very exchanges of matter and energy. Let's first deeply explore how work changes internal energy, specifically focusing on a special process called an adiabatic process. Imagine you have some water in a super-insulated container, like a high-quality thermos flask. This setup is designed so that virtually no heat can pass between your system, the water, and its surroundings. We call such a system an adiabatic system, and any process occurring within it where there's no heat transfer is an adiabatic process. The walls of this container are known as adiabatic walls. They act as perfect thermal insulators.
Okay, adiabatic means no heat in or out. Got it.
Exactly. Now let's step back into history to the pioneering experiments of J.P. Joule in the 1840s and 1850s. His work was pivotal in cementing our understanding of internal energy. Imagine our water system is initially in a state A, with a certain temperature TA and internal energy UA. Joule's first method to change the state. He performed mechanical work on the water. Picture him vigorously stirring the water with paddles inside the insulated container. Let's say he performed 1 kilojoule of mechanical work. He observed a specific temperature rise, reaching TB. The internal energy of the water changed from UA to UB, giving a change UF or U, UB, UA Joule's second method. He then performed an equal amount of electrical work on the same system, say 1 kilojoule, using an immersion rod to heat the water. What was truly remarkable was that he observed the exact same temperature change, reaching the same TB.
The same temperature change from both stirring and heating.
Exactly the same, with the same amount of work done. The profound conclusion from Joule's experiments was this. For a given change of state, the amount of work done to achieve it was always the same, regardless of the method or path by which that work was done. This meant the change in state was independent of the path. This led directly to the formal definition of internal energy as a state function. The adiabatic work, WAD, performed to bring about a change in state is precisely equal to the difference in the internal energy between the final and initial states. So we write, AUU is tantal WAD. This conclusively establishes that internal energy, U, is a state function. Its change depends only on the start and end points, not the journey. Now, let's be absolutely clear about the IUPAC sign convention for work. This is non-negotiable for correct calculations in your exams. W is positive. This signifies that work is done on the system. When the surroundings do work on the system gains energy and its internal energy increases. Think of you compressing a gas in a syringe. You are doing work on the gas, so W is positive.
Okay, W positive, work on the system.
W is negative. This means work is done by the system. When the system performs work on its surroundings, it expends energy and its internal energy decreases. Imagine a gas expanding and pushing a piston. The gas is doing work, so W is negative.
And Drew negative, work by the system. Makes sense.
Now, let's dive into a specific and incredibly common type of work in chemical systems. Pressure volume work, often called mechanical work, which is especially relevant when dealing with gases. Imagine a simple setup. A cylinder containing an ideal gas fitted with a perfectly frictionless piston. Let the gas initially occupy a volume V and its internal pressure be P. Now suppose an external pressure, PEX, is applied, which is slightly greater than the internal pressure. This causes the piston to move inwards, compressing the gas until the internal pressure eventually equals the external pressure and the final volume becomes V. Let's derive the formula for the work done during this compression step by step. Suppose the piston moves inward a tiny distance L, and the cross-sectional area of the piston is A. The change in volume, AV, is simply the final volume minus the initial volume, AV equals VFV. We can also express this infinitesimal volume change as the product of the area and the distance moved, EVAAL. From physics, we know pressure is defined as force per unit area. So the force F exerted on the piston by the external pressure is F equals pex SA. Work, W, is fundamentally defined as force multiplied by the distance moved. So the work done on the system is W force X distance equals pex SAAL. Now here's where we tie it to volume change. For compression, the final volume VF is smaller than the initial volume Vi. This means AV, VFV, will be a negative quantity.
Right, volume decreases, so AV is negative.
Exactly. However, we know from our sign convention that when work is done on the system, compression, W must be positive. To ensure W is positive, given that FVV is negative for compression, we introduce a negative sign into the formula. So we effectively substitute AAL with AAV. Why? Because VFE is negative, multiplying it by -1 makes it positive, correctly reflecting work done on the system. Therefore, the general formula for pressure volume work becomes WV equals pexi, VFO VV. Let's do a quick mental check. If we compress a gas, VF is less than Vi, so VF Vi is negative. A negative multiplied by the negative sign in front makes W positive, which correctly means work is done on the system. If the gas expands, VF is greater than Vi, so VF Vi is positive. A positive multiplied by the negative sign makes WEF negative, correctly indicating work is done by the system. This sign convention is crucial for JEE and NEET. Now, what if the external pressure isn't constant throughout the process, or if the process happens extremely slowly? This introduces the concept of reversible processes, a critical idea in competitive exams. If the external pressure changes in a number of finite steps, the total work done is simply the sum of the work done in each individual step. You can visualize this on a pressure volume PV plot as a series of rectangular areas summing up the total work. But then there's the ideal scenario, a reversible process. A process is said to be reversible if it's carried out in such a way that at any moment it could be perfectly reversed by an infinitesimal change. This implies that the process proceeds infinitely slowly, passing through an infinite series of equilibrium states. At every single point, the system and its surroundings are in near perfect equilibrium. For instance, in a reversible compression, the external pressure, pex, is always just infinitesimally greater than the internal pressure of the gas, pin. So pex equals pin plus dp.
Infinitely slow.
Yeah.
So this is like a theoretical ideal.
Precisely. Any process that doesn't meet these stringent conditions, meaning it's not infinitely slow or doesn't maintain equilibrium states, is termed an irreversible process. In reality, all natural processes are irreversible. For a reversible process, because the external pressure is almost identical to the internal pressure, we can use the internal pressure of the gas, let's just call it P in our work calculation. When the volume changes by an infinitesimal amount, dV, the work done is dP/dV. To find the total work for a finite change from initial volume Vi to final volume V, we perform integration. Rev EPTV from Vi to VZF.
Calculus, okay.
Yes, but don't worry, for the cases you'll see most often, it simplifies nicely. Let's apply this to an ideal gas undergoing an isothermal constant temperature process. For an ideal gas, we know the ideal gas law, PV equals nRT. So we can express pressure P as P as nRTV. Substitute this into our integral for reversible work, Rev nRTV dV from Vi to VF. Since N nonals are gas constant and T temperature are constant for an isothermal process, we can pull them out of the integral, Rev nRT dV from Vi to
Your constant's temp.
And the integral of 1V dV is the natural logarithm, ln A vernal. So the formula for reversible isothermal work becomes Rev nRT ln VFE. If you prefer to work with log base 10, this can be converted using ln x 2.303 log euro. Ben RS equal 2.303 nRT log. This is a critical formula for solving numerical problems involving reversible isothermal processes of ideal gases. You'll see it frequently. Let's consider a very special case of expansion. Free expansion. This occurs when a gas expands into a vacuum. By definition, a vacuum means there is no external pressure to push against. Therefore, the external pressure back is 0.
Okay, pex equals 0 to vacuum.
Exactly. If pex equals 0, then from our general work formula W is kexi EV, the work done becomes W0. This is a key insight. No work is done when a gas expands into a vacuum. Furthermore, for an ideal gas undergoing free expansion, experiments performed by Joule himself showed that there is also no heat transferred. Q will equal 0. Therefore, for the isothermal free expansion of an ideal gas, if both Q and W equals 0, then according to the first law of thermodynamics, which we'll formalize completely next, the change in internal energy EU equals 0 plus 0 plus 0 plus 0. This is a very important result to remember for ideal gases expanding into a vacuum.
So for free expansion of an ideal gas, W0, Q0, and E0, and...
Correct. For an isothermal free expansion of an ideal gas, let's quickly summarize the heat and work relationships for isothermal changes in an ideal gas, as this is a common area for misconceptions. 1. For an irreversible isothermal change, the heat absorbed Q is equal to the negative of the work done, now W, which is given by Q equals the W, equals PEX. Remember, PEX is the constant external pressure it expands against. 2, for a reversible isothermal change, similarly, QW equals nRT ln VFD, or its log-based 10 equivalent, 2.3 nRT log VF now. It's crucial to note that while AU is 0 for any ideal gas isothermal process, the amount of work and heat exchange does depend on whether the process is reversible or irreversible. Reversible work is always the maximum possible work that can be done with a system during expansion, or the minimum work required on the system during compression.
Okay, so reversible work is the maximum work output.
Exactly. For an adiabatic change, where Q equals 0, the change in internal energy is simply equal to the adiabatic work done, AU.
Okay, the sign conventions for work and the idea of reversible versus irreversible processes, especially with that integral form, can feel a bit abstract. Could we maybe walk through some typical exam problems to solidify this?
That's an excellent request, and precisely what we're here to do. Practical problems are the best way to anchor these concepts. We'll go through some textbook examples similar to what you'd face in your board exams and competitive tests. Let's start with problem 5.2. 2 liters of an ideal gas at a pressure of 10 atmometer expands isothermally at 25 degrees C into a vacuum until its total volume is 10 liters. How much heat is absorbed and work is done in the expansion? Now, let's break this down together. The most critical phrase here is expands into a vacuum. What does that immediately tell us about the external pressure, PEX?
Vacuum means there's no opposing pressure, so like PEX is 0.
Exactly. Since the external pressure, PEX, is 0, what does our formula for work done, W ms PEX WV, tell us about the work W in this scenario? And given that it's an ideal gas undergoing isothermal expansion, what did we just discuss about the heat Q for such a process?
If PEX is 0, then W is 0 because anything times 0 is 0. And for an ideal gas undergoing isothermal expansion, Joule's experiments show that Q also equals 0. So if both work and heat are 0, then AU, which is Q plus W, must also be 0. So no work done and no heat absorbed.
Perfectly understood. That's the simplest case, but it's a foundational test of your knowledge. Now, let's subtly change the conditions for problem 5.3. Consider the same expansion from 2L to 10L, but this time against a constant external pressure of 1 atm. What's the immediate difference here that changes our approach compared to the vacuum expansion?
Okay, well, PEX is not 0. It's explicitly given as 1 atm. The volume change EEV is still a 10L final 2L initial equals 8L. That's the same.
Right, so using the work formula WX XY of V, what value do you get for W? And a quick reminder, since this is still an isothermal process for an ideal gas, what can we say about EAU? And AEU equals Q plus W, how does that relate Q and W here?
So W equals 1 atm times 8 L equals 8 liter atto. The negative sign means work is done by the system, which makes sense for expansion. Since area U is still 0 for an isothermal ideal gas expansion, then if area U equal Q plus W, it means 0 Q plus area U plus 8 liter atm. So Q must be plus 8 liter atm. Heat is absorbed by the system.
Very good. See how that simple change in the external condition from a vacuum to a constant external pressure dramatically alters the amount of work done in heat exchanged, even though the initial and final states of the gas are identical? This vividly illustrates that Q and W are path-dependent, while U is a state function. Now let's tackle problem 5.4. Consider the expansion given in problem 5.2 from 2L to 10L, 1 mole of ideal gas at 25 degrees C, but this time the process is conducted reversibly. That word reversibly is your immediate signal for which formula to use for work in an isothermal process. Which one comes to mind?
The one with the logarithm. WA equals to 2.303 nRT log VF.
Precisely. Let's plug in our values carefully. We have N equal 1 mole, R equals 0.08206, L at m O below. This R value conveniently keeps our units consistent for L at m, and T equals 25 degrees C, which is 298 K. VF is 10L, and Bi is 2L. So we're calculating log 1 or 2, which is log 5. What do you get when you calculate log 5 and then the full expression for W?
Okay, let me see. Log 5 is approximately 0.6990. So W equals 2.303, 1.08 298.
Okay, that gives me W 2393.66 now. And because it's isothermal ideal gas expansion, AU is still 0, so Q equals matter W, which means Q plus 393.66 liro. Wow, that's significantly more work done by the system and more heat absorbed compared to the expansion against a constant external pressure.
Excellent. Your calculation is spot on, and your observation about the magnitude is precisely the key takeaway. For the same initial and final states, the amount of work done in heat exchange varies hugely depending on the path taken, whether it's an irreversible expansion against a constant external pressure or a reversible, infinitely slow expansion. This beautifully reinforces the concept of path dependence for heat and work. Now, let's shift our focus to heat Q as another fundamental way to change internal energy. Heat is rigorously defined as the energy exchange between a system and its surroundings solely due to a temperature difference and without any work being done. Imagine a simple scenario. You have water in a container made of a thermally conducting material like a copper beaker, and you place it into a much larger body of water maintained at a different temperature, a heat reservoir. If the reservoir is hotter, heat will flow into the water in your beaker. Crucially, if you keep the volume of your system constant, meaning AV, so no PV work is done, then any change in the system's internal energy will be directly equal to the heat absorbed. We denote this as AVU equals QV. This subscript V here is a reminder that the heat transfer happened under constant volume conditions.
Okay, QV for constant volume heat.
Right. Again, let's reinforce the IUPAC sign convention for heat. Q is positive. This means heat is transferred from the surroundings to the system. When the system absorbs heat, an endothermic process, its internal energy increases.
Q positive, heat in.
Q is negative. This means heat is transferred from the system to the surroundings. When the system releases heat, an exothermic process, its internal energy decreases.
Q negative, heat out. Got it.
Now that we've separately explored how internal energy can change through work and through heat, let's bring it all together for the general case and the first law of thermodynamics. This is foundational. When a change occurs in a system that involves both heat transfer and work being done, the change in internal energy of that system is simply the sum of the heat, Q, and the work, W. This is the fundamental mathematical expression of the first law of thermodynamics. Work OU equals Q plus W, equation 5.1. Here's the profound insight. While Q and W individually are path-dependent, as we saw in our example problems, their sum, Q plus W, is always equal to U. And because U is a state function, its value will only depend on the initial and final states of the system, making it completely independent of the path taken. This is a powerful statement about the nature of energy itself.
So even if Q and W change depending on the path, their sum, AU, is always the same between two states.
Exactly right. That's the essence of it. Consider an isolated system, which, as we defined earlier, experiences no exchange of energy or matter with its surroundings. In such a system, both work, W, and heat, Q, are 0. Therefore, for an isolated system, U equals 0, 0. This means the internal energy of an isolated system remains constant. This leads us directly to the core statement of the first law of thermodynamics. The energy of an isolated system is constant. This is also widely known as the law of conservation of energy, a principle you've likely encountered before. Energy can neither be created nor destroyed. It can only be transformed from one form to another. It's truly a universal law. An important note for your conceptual clarity. While we can precisely measure changes in internal energy, we cannot measure the absolute value of a system's internal energy. Thermodynamics is primarily concerned with these measurable changes. Let's put this fundamental first law to immediate use with a quick problem, problem 5.1, which asks us to express the change in internal energy under different conditions and identify the system or wall type. This is a common way to test your understanding of definitions and conventions. Part I states, no heat is absorbed by the system from the surroundings, but work, W, is done on the system. What type of wall does the system have? So, if no heat is absorbed, what does that mean for Q? And if work W is done on the system, what's its sign? Finally, based on the heat condition, what kind of wall must be present?
Okay, no heat absorbed means Q equals 0. Work done on the system, so W would be positive. That means the first law, AU equals Q plus W, simplifies to EUW. And a wall that prevents any heat transfer. That's an adiabatic wall.
Perfectly right. That describes an adiabatic process where EU equals the adiabatic work. Excellent. Now, for part 2, no work is done on the system, but Q amount of heat is taken out from the system and given to the surroundings. What type of wall does the system have? What does no work done imply for W? And if heat is taken out from the system, what's the correct sign for Q according to IUPAC convention? And what kind of wall allows this heat to transfer?
Okay, no work done. W equals 0. Heat taken out means the system loses heat, so Q would be negative. Therefore, AU plus W becomes AEU equals to Q. For heat to be transferred, the walls must be thermally conducting walls.
Excellent. You've got the sign conventions and the wall types perfectly aligned. Moving to part 3. W amount of work is done by the system, and Q amount of heat is supplied to the system. What type of system would it be? Quiz. First, let's get the signs right. Work is done by the system. What sign is that? And heat is supplied to the system. What sign is Q in that case? And finally, what kind of system exchanges both energy through heat and work, but not matter?
Work done by system means W is negative, so we write it as BW. Heat supplied to the system means Q is positive. So the first law gives us AU, U is QW. This scenario where energy is exchanged but matter is not, that describes a closed system.
Fantastic. You're grasping these conventions and their implications for system types very well. This problem, though seemingly simple, encapsulates core thermodynamic principles you need for your exams. Now let's move to a very practical challenge. While NEU is perfect for processes at constant volume, most chemical reactions we carry out in the laboratory or in industry happen at constant atmospheric pressure, not constant volume. So we desperately need a new tool, a new state function, to easily quantify heat changes under these common constant pressure conditions. This brings us to enthalpy, AD. Let's define enthalpy and understand why it's so incredibly useful. We start with our fundamental first law of thermodynamics. NEU will plus W. When a process occurs at constant pressure, the work done, specifically pressure volume work, is given by W to be AV. Here, Q is the heat absorbed or released at constant pressure, which we specifically denote as QP.
QP for constant pressure heat.
Okay. So substituting W equals APV into the first law equation, we get APUU. Now let's rearrange this equation to isolate QP, as this is the quantity we're interested in measuring at constant pressure. QPU plus PV. To make this definition universally applicable, let's consider the system's initial state as 1 and its final state as 2. So EU, EPUU, and APERO equals VO. Substituting these into our rearranged equation for QP, QPO equals UERO plus PVVO. Now for a bit of mathematical elegance, let's rearrange the terms on the right side by grouping them. QPU plus PV, AP plus PVO. This natural grouping leads us directly to the definition of our new thermodynamic function, enthalpy. Enthalpy is defined as HU equals U plus PV, equation 5.7. Since U, internal energy, P, pressure, and V, volume, are all state functions, meaning their values depend only on the current state, not the path, H must also be a state function.
So H is also a state function. That's important.
Hugely important. This means any change in enthalpy is therefore also independent of the path taken. Now, substituting our definition of H back into the equation for QP, we arrive at a profound and incredibly useful result. QP equals HHOAH. This means the heat absorbed or evolved by a system at constant pressure is precisely equal to the change in its enthalpy. This is why enthalpy is such a workhorse in chemistry, because most reactions in the lab occur open to the atmosphere at constant pressure. For any finite changes occurring at constant pressure, we can write the relationship as HAU plus PAV, equation 5.8. The key takeaway for your exams is this. When you perform a chemical reaction in an open beaker and measure the heat absorbed or evolved, you are directly measuring the change in enthalpy for that reaction. Remember the signs. Exothermic reactions, these reactions release heat to the surroundings. Therefore, QP is negative, and thus H is negative. Think of burning fuel, heat comes out.
Exothermic, H negative.
Endothermic reactions. These reactions absorb heat from the surroundings. Therefore, QP is positive, and thus EH is positive. Think of an ice pack. It absorbs heat to get cold.
Endothermic, AH positive, right?
Yeah.
So EH is basically the heat change we measure in a typical open-air experiment. And that relationship in the H plus PA is really critical.
Exactly. You've perfectly captured its essence. AH is indeed that everyday heat change we observe at constant pressure. And yes, the relationship AHE plus pi of V is not just critical, it's one of the most frequently tested equations in chemical thermodynamics for JEE and NEET. Now let's explore when the difference between AHAU becomes significant, because sometimes they're nearly identical and sometimes they're quite different. When we're dealing with reactions that involve only solids and/or liquids, the volume changes that occur during the reaction are usually minuscule, almost negligible. Imagine melting ice or dissolving salt. The overall volume change is typically very small. In these situations, the pi of V term in our AHU plus pi of V equation becomes approximately 0. Consequently, for reactions involving only solids and liquids, AHE. So for these types of reactions, the distinction between enthalpy and internal energy changes isn't a major concern for calculations.
Okay, so for solids and liquids, AH and EU are pretty much the same.
Generally, yes, for practical purposes. However, the difference between EH and UU becomes very significant and must be accounted for when gases are involved, because gases can undergo very substantial volume changes. Let's derive the precise relationship for reactions that produce or consume gases. Consider a general gaseous reaction occurring at constant pressure and constant temperature T. Let Na represent the total number of moles of gaseous reactants and Nb represent the total number of moles of gaseous products as determined by the stoichiometric coefficients in the balanced chemical equation. Using the ideal gas law, PV equals nRT, we can write, for the gaseous reactants, PVA equals NART. And for the gaseous products, PVB, NBRT. Now subtract the reactant equation from the product equation. PVB, PVA, NBRT, NART. Factor RP on the left and RT on the right. PVBA equals NBS, NBNA. The term VBVA is simply the change in volume, NV. The term NBNA is the change in the number of moles of gaseous substances during the reaction. We denote this as M. Remember, ND only includes gaseous species. Solids and liquids do not contribute to Ang.
Only the gases matter for Ang.
Exactly. So we get this extremely useful relationship, PAV-INRT, equation 5.9. Now, we can substitute this expression for AV back into our fundamental enthalpy equation, AHUU plus AAV. This gives us the final critical formula, AHU plus AART, equation 5.0. This equation, AAHU plus AART, is a must-know for calculating AJs from a E or vice versa, especially in reactions where gases are produced or consumed. It's an absolute favorite for competitive exams like JEE and NEET, so practice its application well. Let's immediately apply this crucial formula to a problem, problem 5.5. If water vapor is assumed to be a perfect gas, the molar enthalpy change for vaporization of 1 mole of water at 1 bar and 100 degrees C is 41 kilojoules in LO. Calculate the internal energy change when 1 mole of water is vaporized at 1 bar pressure and 100 degrees SPIA. Let's break this down systematically. The process is the vaporization of water, HEHOG. Our first step is to determine AH. How many moles of gaseous product do we have, and how many moles of gaseous reactant? Remember, only count the gases.
Okay, so on the product side, we have 1 mole of HEO. On the reactant side, HOL is liquid, so it doesn't count for H. Therefore, 1 mole in gaseous product, mole of gaseous reactant. OL.
Perfect. Now, we use our derived formula, AHEOART. We are given EH equals 41.00 gauge mole. The gas constant R is 8.314 J mole, and the temperature T is 100 degrees C, which we must convert to Kelvin. 100 plus 273 equals 30873 K, a crucial point for calculations. Notice that Ag is given in kilojoules per mole, kJ mole, but R is typically in joules per Kelvin per mole. J mole must convert the R day term to kilojoules to ensure consistency in our final answer. So 8.314 J is 0.008314 kilogram.
Right, units must match. So let's calculate the E and RT term first in kJ. E and RT equals 1 mole, 0.08314 keto mole to tito, the J equals 3.096 kiloj mole.
Excellent. Now complete the calculation by subtracting this value from EH.
So AU 41.0000 kilomole. This shows the internal energy change is slightly less than the enthalpy change. That makes perfect sense. When water vaporizes, it expands against a constant atmospheric pressure, doing work. So some of the heat energy supplied isn't just increasing the internal energy, but also performing that expansion work.
Exactly. This is a classic application on the formula and truly highlights the physical meaning behind the difference between AA and AU. This type of problem is a frequent visitor in competitive exams, so internalize it well. Let's take a brief detour to differentiate between two crucial types of properties that describe thermodynamic systems: extensive and intensive properties. This distinction is very commonly tested in multiple choice questions. An extensive property is one whose value depends directly on the quantity or size of the matter present in the system. Think of it this way. If you double the amount of substance, the extensive property will also double. Classic examples include mass, total volume, internal energy, d enthalpy U, and total heat capacity, C. They all scale up with the amount of material.
Extensive scales with amount, okay.
In contrast, an intensive property is a property whose value does not depend on the quantity or size of the matter present. If you take a portion of the system, this property remains the same. Examples include temperature, T, density, and pressure.
Intensive doesn't depend on amount, like temperature.
Precisely. Let's illustrate with a simple mental experiment. Imagine a large container filled with a gas, initially at a volume V and temperature T. Now, suppose you introduce a thin imaginary partition right down the middle, conceptually dividing the gas into two equal halves. Each new half system now has a volume of V2. Since the volume has changed proportionally to the amount of gas in that part, volume is clearly an extensive property. However, what about the temperature? The temperature in each half will still be T, assuming no heat transfer. The temperature hasn't changed simply because you conceptually divided the volume. This elegantly demonstrates that temperature is an intensive property. An important related concept is a molar property. This is simply an extensive property divided by the amount of substance it involves. By dividing by the amount, you normalize the property, making it an intensive property. For instance, molar volume, Vm, or molar heat capacity, CMEN, are intensive properties because they are properties per mole of substance. This is a neat trick.
So extensive properties depend on how much stuff you have, but intensive ones are fixed for the substance itself, regardless of quantity.
That's the perfect, concise way to summarize it. You've grasped that key distinction very well. Now, let's explore how we quantify heat transfer by measuring temperature changes, which leads us to the concept of heat capacity C. The fundamental concept here is quite intuitive. When you add heat to a system, its temperature usually rises. The increase in temperature is directly proportional to the amount of heat transferred. We express this relationship with a simple equation, Q equals C AT. Here, the coefficient C is what we call the heat capacity. Its numerical value depends on several factors: the size of the system, how much substance is there, its chemical composition, what it's made of, and its specific nature. The implication of this definition is important. If a substance has a large heat capacity, it means that a given amount of heat will result in only a small temperature rise. Think of water, which has an unusually large heat capacity. This is why it takes so much energy to boil water, and why large bodies of water help moderate climate.
Right, water takes ages to heat up, high heat capacity.
Exactly. We also have more specific terms related to heat capacity, which you'll encounter in problems. Molar heat capacity, CM. This is the heat capacity for 1 mole of a substance. It's the quantity of heat needed to raise the temperature of 1 mole of that substance by 1 degree Celsius, or 1 Kelvin. Specific heat C, or a specific heat capacity. This is the quantity of heat required to raise the temperature of 1 unit mass of a substance, typically 1 gram, by 1 degree Celsius, or 1 Kelvin.
Okay, molar heat capacity is per mole, specific heat is per gram.
Correct. So when you need to calculate the total heat Q required to raise the temperature of a specific sample, you can use one of these two formulas depending on what's given. Q equals C MAAT, specific heat multiplied by mass and temperature change, or more generally, Q equals C, total heat capacity multiplied by temperature change. Both are widely used in numerical problems. Building on the concept of heat capacity, let's derive a very important relationship specifically for an ideal gas: the relationship between CP, heat capacity at constant pressure, and CV, heat capacity at constant volume. This relation, CP-CVR, is a foundational piece of knowledge often tested directly or indirectly in JEE and NEET. We've already established that when heat is supplied at constant volume, the heat capacity is denoted by CV, and it relates to the change in internal energy, QV equals UU. Therefore, we can say CV equals ETV, which we simplify to do ET for finite changes at constant volume.
Say CV relates to U.
Similarly, when heat is supplied at constant pressure, the heat capacity is CP, and it relates to the change in enthalpy, QP equals your H. Therefore, we can say CP HHTP, simplified to Ereche for finite changes at constant pressure.
And CP relates to Ereche.
Exactly. Now, let's derive the relationship between CP and ECV for a single mole of an ideal gas, step by step, making it easy to follow. We know the fundamental definition of enthalpy, H equal U plus PV. If we consider a change in enthalpy, HA equals APB for 1 mole of an ideal gas, the ideal gas law states PV equals RT. So we can substitute RT for PV in our change in enthalpy equation, EP on or HA plus RC. Since R, the ideal gas constant, is by definition a constant, the change in RT can simply be written as R multiplied by the change in T at H plus RTB plus RAT10. Now, to get to the heat capacities, which involve changes with respect to temperature, let's divide the entire equation by a T, HRT plus RT. Now, we can substitute our definitions of CP and CV from earlier, CP equals CV plus R. And finally, rearranging this, we get a very famous and practical relationship, CP-CV-R, equation 5.13.
CP minus CV equals R. That's the one.
That's the one. The significance of this relationship is profound and often asked in viva or conceptual questions. CEP is always greater than CV for a gas. Why? Because at constant pressure, when you add heat to a gas, some of that energy is used not just to increase the gas's internal energy, like increasing its temperature, but also to do expansion work against the external atmosphere, that PEV term. This means that to achieve the same temperature rise, you need to supply more heat at constant pressure than you would at constant volume, where no expansion work is done. The difference in the heat supplied is precisely equal to the energy required to do that expansion work, which is elegantly captured by the gas constant, R. This is an extremely important relation you'll use constantly in problems, so commit it to memory. Now that we've grasped the theoretical concepts of EU and EOH, the next crucial step, particularly for your practical understanding in exam questions, is understanding how we actually measure these energy changes experimentally. This is where the powerful technique of calorimetry comes in. Calorimetry is the experimental art of measuring heat changes that accompany chemical or physical processes. The process is carried out inside a specially designed vessel called a calorimeter, which is usually immersed in a known volume of a liquid, typically water. By knowing the heat capacity of both the liquid and the calorimeter apparatus itself, we can determine the amount of heat evolved or absorbed in the process simply by meticulously measuring the temperature changes.
So you measure the temperature change of the water bath, basically.
Essentially, yes, of the water bath and the calorimeter itself. These measurements are primarily made under two distinct conditions, corresponding to our definitions of internal energy and enthalpy. 1. At constant volume, QV, which directly yields U2, at constant pressure, QP, which directly yields UH. Let's start with UAU measurements, which are most accurately performed using a bomb calorimeter. This apparatus is specifically engineered to measure heat changes under conditions of constant volume. Picture a bomb calorimeter. It consists of a robust, sealed steel vessel, often colloquially called the bomb. This bomb is hermetically sealed and then immersed in a carefully insulated water bath. The entire assembly, the bomb, the water bath, and its precise temperature measuring devices constitutes the calorimeter. The design ensures that any heat evolved during the reaction inside the bomb is transferred completely to the surrounding water, with minimal loss to the external environment.
Okay, so it's sealed tight, constant volume.
Exactly. Here's how a typical experiment works. A known mass of a substance, usually a combustible one, is placed inside the steel bomb. The bomb is then sealed and filled with pure oxygen under high pressure. Once prepared, the substance is ignited electrically. It burns completely, combusts within the bomb. The heat released by this combustion reaction warms the surrounding water, causing its temperature to rise. This temperature increase is meticulously monitored. Because the bomb calorimeter is a sealed, rigid vessel, its volume remains absolutely constant throughout the reaction, meaning OV equals 0. Under these constant volume conditions, no pressure volume work can be done. Therefore, according to the first law, UU plus W, the heat evolved or absorbed inside the bomb calorimeter QV is entirely and precisely equal to the change in the internal energy of the system. So the measured heat, QV, is exactly UU. The calculation is relatively straightforward. We use the formula calorimeter, C calorimeter T, where C calorimeter is the known heat capacity of the entire calorimeter assembly, and C cal is the measured temperature rise. The heat of the reaction itself, reaction, will then be the negative of the heat absorbed by the calorimeter, because heat lost by the system equals heat gained by the calorimeter.
Heat lost by reaction equals heat gained by calorimeter. Makes sense.
Let's apply this to a classic bomb calorimeter problem, problem 5.6. 1 gram of graphite is burnt in a bomb calorimeter in excess of oxygen at 298 K and 1 atmospheric pressure, according to the equation C, graphite, plus OG. During the reaction, the temperature rises from 298 K to 299 K. If the heat capacity of the bomb calorimeter is 20.7 kJK, what is the enthalpy change for the above reaction at 298 K and 1 at mm? Let's break this down step by step, just like you would in an exam. First, calculate the heat absorbed by the calorimeter. What's the formula in the calculation?
Okay, heat absorbed by calorimeter. Calorimeter is C calorimeter times the AT. So calorimeter 20.7 kilojoules, O, 290, and K, or 290 K equals 20.7 kiloj.
Excellent. Now remember our sign convention and the purpose of the calorimeter. The heat evolved from the reaction. Reaction will have the same magnitude but the opposite sign. Why is that, and what is the value of reaction? And what does this tell us about UO2 for the reaction?
Right, so reaction equals started than 20.7 kilojoules.
Yeah.
It's negative because the reaction released heat. It's exothermic. And since this is a bomb calorimeter operating at constant volume, this reaction is directly equal to LU for the combustion of 1 gram of graphite.
Perfectly explained. So LU for the combustion of 1 gram of graphite is negative to 20.7 kiloj. But the problem asks for the enthalpy change per mole. What's the molar mass of carbon in graphite, and how do we convert our LU value to kJ per mole?
The molar mass of carbon is 12 kilomole. To convert negative 2.7 kilojoules per 1 gram to per mole, we multiply by 12 kilomole. Negative 20.7 kiloj at 1 g, 12 kilomole. Negative 248.4 kiloj moleo. So LU for 1 mole of graphite combustion is negative 248.4 kiloj moleo.
Excellent. Now for the crucial final step, Relate this LU value to LUH, as the question specifically asks for LUH. What's the formula that connects LU for reactions involving gases? And specifically for this reaction, C graphite plus OG, what is it? The change in the number of moles of gaseous products minus gaseous reactants.
The formula is EHOE plus OAU. For the reaction, C graphite is solid, so it doesn't count for ER. We have 1 mole of OG as reactant and 1 mole of co-urea product. So Yang only gaseous product, 1 mole gaseous reactant equals 0.
And if Yang equals 0, what does that directly imply about the relationship between REH and U?
If Yang equals 0, then the entire ERE on RT term becomes 0. So ERE on U. Therefore, EA for the combustion of graphite is also negation 248.4 kilodiamole.
Absolutely perfect. This problem beautifully illustrates the entire sequence, how to use bomb calorimetry to find EU, and then how to apply the EH versus E relationship to arrive at the final HH. This is a very common and important question type. Now, let's look at EH measurements, which are often simpler to conduct and are much more common because they happen at constant pressure, typically open to the atmosphere. Measuring heat changes at constant pressure, QP, can be done using a simpler type of calorimeter, often just an insulated vessel open to the atmosphere, sometimes called a coffee cup calorimeter. As we discussed, when a process occurs at constant pressure, the heat absorbed or evolved, QP, is directly equal to the change in enthalpy, EH. Therefore, we can simply state EAH QP. This measured heat is also frequently referred to as the heat of reaction or the enthalpy of reaction, AH. The signs for ARH follow our established conventions. Exothermic means QP negative, ARH negative. Endothermic means QP positive, AAH positive.
Okay, so coffee cup calorimeter gives each directly. Much simpler.
Generally, yes, for many solution-based reactions. Moving beyond direct measurement, let's talk about the enthalpy change of a reaction in a more general and calculable sense. This is simply the enthalpy change that accompanies a given chemical reaction where reactants are converted into products. We represent it broadly as reactants, A products. The enthalpy change of a chemical reaction, AARH, is calculated as the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. This can be concisely expressed by the formula ARH, apol or IIH products, AAH reactants, equation 5.14. Now, don't let the summation symbol intimidate you. It simply means add up. So you add up the molar enthalpies of all the products, each multiplied by its stoichiometric coefficient, and subtract the sum of molar enthalpies of reactants, each multiplied by its coefficient.
Products minus reactants, weighted by coefficients. Got it.
Exactly. Knowing RAH is incredibly useful not just for exams, but for real-world applications like industrial process planning, heating, cooling, and calculating temperature dependence of equilibrium constants. To make our calculations comparable and meaningful across different experiments and studies, especially in competitive exams, we use standard enthalpy of reactions, RAHR. The enthalpy of a reaction can vary depending on the conditions. So, to standardize our data, we define the standard enthalpy of reaction as the enthalpy change for a reaction when all the participating substances are in their standard states. What exactly is a standard state? For a substance, its standard state at a specified temperature is defined as its pure form at exactly 1 bar pressure. While the temperature can technically be any temperature, most standard enthalpy data you'll encounter are typically given at 298 K, 25 degrees C. The notation for standard conditions is a superscript degree symbol, so we write it as REH. This simple symbol indicates that all substances are in their defined standard states.
Standard state, 1 bar, pure form, usually 298 K.
That's the key definition. Now let's discuss enthalpy changes during phase transformations. These are physical changes, like melting or boiling, but they involve significant energy changes. Think about melting ice, boiling water, or dry ice subliming. All these transformations fundamentally involve heat absorption from the surroundings. Since they typically occur at constant atmospheric pressure, these heat changes are enthalpy changes, and they are always positive, endothermic for melting fusion, vaporization, and sublimation. Let's define a few key terms. Standard enthalpy of fusion, FSHAs. This is the enthalpy change when 1 mole of a solid melts completely into its liquid form in its standard state, usually at its normal melting point. Example, AFHHS, AFSHA, plus 6.000 J Nolo Burko at 273 K. Freezing is the reverse, HH is negative.
Fusion is melting, endothermic.
Standard enthalpy of vaporization, AFHH. This is the amount of heat required to vaporize 1 mole of a liquid at constant temperature, boiling point, and standard pressure. Example, HO air, FHA. AFAPH plus 40.79 kilojmole at boiling point.
Vaporization is boiling, also endothermic.
Standard enthalpy of sublimation. This is the change in enthalpy when 1 mole of a solid sublimes, solid to gas, at constant temperature and standard pressure. Example, Solid Kyo, dry ice, at 195 K. A sub H equals 25.2 kJ/mol. The magnitude of these enthalpy changes largely depends on the strength of the intermolecular interactions. Stronger forces mean higher enthalpy changes are required. Water has strong hydrogen bonds, needing more energy to vaporize than acetone with weaker forces.
Stronger forces, higher AGE for phase change. Makes sense.
Let's apply these concepts to a practical scenario with problem 5.7. A swimmer coming out from a pool is covered with a film of water weighing about 18 bal. How much heat must be supplied to evaporate this water at 298 K? Also, calculate the internal energy of vaporization at 298 K. Evap H for water at 298 K equals 44.01 kJ/mol. First, we need the number of moles of water. We're given 18 bal. What's the molar mass and how many moles is that?
Molar mass of HO is 18 mol, so 18 jam is exactly 1 mole.
Correct. So the heat supplied to evaporate 1 mole of water at 298 K is simply the number of moles multiplied by the standard enthalpy of vaporization. Go ahead and calculate that.
Okay, heat supplied 1 mole, ABA 44.01 kJ. Mole wall equals 44.01 kJ. This is the heat needed, which is ap each.
Excellent. Now for the second part, calculating the internal energy of vaporization, which formula relates your H considering the phase change?
We should use the formula RT for vaporization. ELIOE is 1 mole of gas minus 0 mole of gas, so RR11.
Very good. Now plug in the values. 44.01 kilojoules aero, R 8.31 or J kilomole. T, remember the unit conversion for RT to KJ.
Okay, RDH 8.31 Gore, X 298 K equals 2477.572. J converting to KJ, that's 2.477 kiloj. Now, air is 44.01 kiloj mole. 2.477 kiloj mole. So it's 44.577 kiloj.
Precisely. So the internal energy change is slightly less than the enthalpy change, accounting for the work done by the system against the atmosphere during expansion. This is subtle but important. Let's tackle another common multi-step problem, problem 5.8. Calculate the internal energy change when 1 mole of water at 100 degrees C and 1 bar is converted to ice at 0 degrees C, given FSH equals 6.00 kJ/mol at 0 degrees C, and heat capacity of water is 4.2 j/degree C. This is a typical JEE level problem requiring breaking it down. We need to go from liquid water at 100 degrees C to solid ice at 0 degrees C. 2 steps. Step 1 mole HO, 1 mole aero, 0 degrees C. 1 mole in aeros, 0 degrees C, freezing liquid water. Finally, air's total NFE change, A total AO plus JOs.
Okay, cooling then freezing.
Let's calculate RACER. First, heat lost when 1 mole 18 gram of water cools from 100 degrees to 0 degrees. Use Q mole CNC.
Okay, Holland's 80 arrows, East 18 degrees, C degrees, 100 degrees, 90 degrees, 1 degrees, 0 degrees, degrees over 80, 5 degrees, 100 degrees, Z, 80 degrees, Z by actually, minus C, many degrees, C. Near D is 80 to 4.2 J degrees 0, so 80 over 4.2 J degrees C, grade 7276 DC. Converting to Ker J, that's 907.56 kJ/1 alien 4.
Correct. Negative sign means heat released. Now, for AH, freezing at 0 degrees C, we're given enthalpy of fusion, melting, is plus 6.00 kiloj/mol. What's the sign and magnitude for freezing?
Freezing is the reverse of fusion. So if fusion is endothermic plus 6.00, then freezing must be exothermic. Negative 6.0 kiloj/mol.
Excellent. Now, sum these two to find the total AH.
Total RAs plus NH is NA is 6.6 kiloj/mol, NAD is 6.000 J-molar up, plus NAD is 6.56 kiloj/mol.
Very good. The final part asks for the internal energy change. For the process liquid to solid, is the POV term significant, or N?
No, not really. Solids and liquids have negligible volume changes compared to gases. There are no gases involved, so M angles 0. This means the PV term is approximately 0.
Precisely. So when PV is 0, what's the relation between GABA UMO?
Then the GABA UMO, so NMO is 13.56 kiloj/mol.
Fantastic. This problem combines cooling and phase transitions, a common pattern. Practice breaking down such multi-step problems. Let's move on to another crucial type of enthalpy. Standard enthalpy of formation, HH. This concept is fundamental for calculating reaction enthalpies using tabulated data. The standard enthalpy of formation, FH, is strictly defined as the enthalpy change when 1 mole of a chemical compound is formed from its constituent elements in their most stable states of aggregation, their reference states, under standard conditions. 298 K, 1 bar. Let's clarify. Most stable states, or reference states, Hg, Og, C graphite, S rhombic, S, etc.
Right, the most common form of the element.
Examples: Hg plus Au, HOL. A share alanical tonnage 285.8 kiloj/mol. 1 mole water from elements in standard states. C graphite S plus 2HRO, HAOF, H initial 74.81 kiloj/mol. 1 mole methane from elements. Now, an important distinction for exams, it's not if H or if formed from compounds or if more than 1 mole is formed. Example, CaO plus CuHA. Not if H of cacose because it's from compounds. Example, Hg plus BrO. Not if H of HBr because 2 mole is formed. Need to divide by 2.
Ah, okay. It must be 1 molar product from elements in standard states. Very specific definition.
Very specific. By convention, the standard enthalpy of formation of an element in its most stable reference state is defined as 0. Half-off-white C, graphite is 0. This provides a baseline. The true power of accept values is calculating Ehr-Hoffet for any reaction using half-off-white, half-off reactants, equation 5.15. Sum of formation enthalpies of products times their coefficients minus sum of formation enthalpies of reactants times their coefficients. Let's apply this. Decomposition of Kopheit-EO plus Su-ERO. How would you set up the formula? Okay, Ereco E, 1 arrow F, Hoffite, Offite, 1 arrow F, Hoffite. Correct. Now, using typical values provided in exams of Hoffite, Ninja 635.1 kilograms. If F55, Ninja 393.1 kilograms. FX, Offite, Oro, Ninja 393.1 kilograms. FX, Offite, 12 or 6.9 kilogram. I'll plug these in carefully. Okay, so Hafaf, Afasaiva is 635.1 plus Ninja 393.5, Ninja 1 or 96.9, Ninja 1 there of 28.6 plus 128.6.9 plus 178.3 kilograms.
Excellent. Perfect calculation. What does the positive sign tell us about this reaction?
Positive aerature means it's endothermic. You need to supply heat, like heating limestone in a kiln.
Exactly. This is how chemists predict energy requirements. This formula is incredibly powerful and frequently tested. Now let's look at thermochemical equations. A thermochemical equation is a balanced chemical equation that includes 1. The value of its standard reaction enthalpy, ARHO. 2. The physical state, SLGAQ, for every substance, allotrope specified 2. Example, COHOL plus 3OJ, CuCOAO plus 3HOL. ARHA is 9 hours 1,367 kJ/mol. Tells us liquid ethanol combustion releases 30 or 367 kJ per mole ethanol as written. Important conventions for working with these. 1. Coefficients moles. 2. ARHA value is for moles specified in the equation. 3. Reversing a reaction reverses the sign of ARHO. Example, M plus 3HRO, 2 NEHs, ARHA JO plus 91.8 kJ. Reverse, 2 NERs, ARSM plus 3H, ARTH plus 91.8 kilojoules.
Flip the reaction, flip the sign. Easy enough.
4. AH is extensive. Multiply coefficients by a factor, multiply A or H by the same factor. Have the equation, have the ARHs. These conventions are vital for applying our next big concept, Hess's law of constant heat summation. This is a powerhouse tool. Hess's law comes from enthalpy, H being a state function. AH is independent of the path. Total enthalpy change is the same whether it's one step or multiple steps. Hess's law states, if a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided.
So you can add up enthalpy changes of steps to get the overall enthalpy change.
Precisely. It's incredibly important because it allows calculation of EH for reactions hard to measure directly. Let's illustrate with a classic example. C, graphite ARH plus Hafo-Urers COG. Hard to measure directly because CoUrers is also formed. But we know I, C, graphite plus Hog-Urers, ARH, Honning is 393.5 kJ/mol. COG plus HOG is air 8 is 283.0 air/mol. We want CO as a product. Look at equation 2. What should we do? And what happens to its area?
We need to reverse equation 2. And when we reverse it, the sign of AREO slips. So 3 plus AREOs becomes plus 283.0 euro/mol.
Perfect. Now add equation A and our modified equation 3. Sum them up and cancel common terms.
Okay, adding I and 3, C graphite plus EO plus COG plus ARG on both sides. OG on left is 1 mole, on right is half mole, so ARG remains on left. Simplified CO plus AREs. That's our target.
Brilliant, exactly. Now the final Hess's law step. Sum the ARH values of I and 3.
Total air sum I plus air from 3. Nugan is 393.5 kJ/mol plus 283.0 kJ/mol. Wow, that's really clever. We found it indirectly.
It truly is a powerful application. This is a classic Hess's law problem, a sure shot for board exams and competitive tests. Now let's talk about enthalpies for different types of reactions. We often give specific names to ARH changes. First, standard enthalpy of combustion. Combustion reactions are exothermic, release heat. S agrees is the enthalpy change when 1 mole of a substance undergoes complete combustion with oxygen with all reactants products in standard states. ARES is always negative. Example, CHL plus 6 COD plus 3 ARG plus 3 A share 1 mole liquid benzene combustion. Let's apply Hess's law again using combustion data. Problem 5.9. Combustion of 1 mole benzene at 298 K liberates 300 and 267 kJ-OA. Given Menthol, F is Sherrero, Essek of 393.5 kJ-MOLO, and H over nitrogen and they turn 85.83 kJ-MOLO. Calculate air of benzene. This is Hess's law in disguise. Target is formation benzene. I6C graphite plus 3H arrow, F-ish O air.
CH arrow plus 6 euros plus 3 arrows plus 3H arrows 267 kJ-MOLO. Negative sign well 3. Formation coheros. C graphite plus OG. AH air equals 383.5 kJ-MOLO. Formation H arrow. HG plus H arrow. 8 arrow. O is 285.83 kJ-MOLO.
We need 6C and 3 HOs on the reactant side. Modify 3 and 4. What do we do?
Multiply 3 by 6 and 4 by 3.
6C graphite plus 6 euros, 6 euros, 6 euros, 3.5 narrows, 261 kJ.
3H euros plus 3H euro plus 3H or 3 handers is 285.83. Sum equations and VH values.
Okay, adding them.
6C euro plus 3 OG plus 6 plus euro C, 6C OG plus 3H euro plus 3H euro plus 3H euro. Oxygen is 122 plus 32.
6 euro 5 plus 3H euro, 6 euro plus 3H euro plus 3H euro. Oxygen is 122 plus 32.
Very good. Now look at target. We need CH as a product. In equation 2, it's a reactant. What do we do with 2? Reverse equation 2 and flip the sign of HECUA plus 3H euros plus HEA euros plus 3H2 and 66 killer.
Perfect. Final step. Add equation V and 6. Cancel common terms. This should give target high some HV and HV.
Add HEH, like 6H graphite plus 3H euros, 1 T euros plus 3H euros is 60 euros plus 3H euros plus 3H euros plus TH euros plus 3H euros. Cancel terms, HEO 60 euros. Leave 6C graphite plus 3H euros as target. HEHO plus V minus 300, 200, 218.49 kJ plus 3H 67 kilojoules plus 48.51 kJ mole.
That's it. A brilliant application of Hess's law. These multi-step problems are exam favorites. Next, enthalpy of atomization. Example. This is the enthalpy change when 1 mole of a substance breaks down completely into its constituent atoms, all in the gaseous phase. Example. HEGO 3H2O is a HEG pile G, HEGO0 plus 4HG equals bond dissociation enthalpy here. Example, GHEV plus 4HG equals 1665 kJ-mol breaking all 4 CH bonds. Example, NES, HEO, 108.4 kJ-mol equals sublimation enthalpy here. Products are always gaseous atoms.
Okay, atomization means breaking everything into gas phase atoms.
Precisely. Closely related is bond enthalpy. E bond HE. Chemical reactions involve breaking old bonds, requires energy, and forming new bonds releases energy. We distinguish. 1. Bond dissociation enthalpy, breaking one specific bond. For diatomics like HG, 2HG, HEH, Eric's equals 435.0 J mole. 2. Mean bond enthalpy. For polyatomic molecules like CH, breaking each CH bond requires slightly different energy. 2. Mean bond enthalpy, CHG plus HG. A bond H equals plus 427 kilobernal. 2. Mean bond enthalpy, CHG plus HG plus 439 kilodonal, etc. Total atomization, CHE plus 4HE, HEH Eris plus 4OFB, and 1665 kiloj, H arrow looks 416 kiloj mole. This is an average value.
So mean bond enthalpy is an average for a type of bond in a molecule.
Yes, a useful average. We can estimate reaction enthalpy using bond enthalpies, especially for gas phase. Air A sure bond enthalpies, reactants, bond enthalpies, products. Equation 5.17. Energy absorbed to break reactant bonds minus energy released forming product bonds. It's an approximation.
Reactants minus products for bond enthalpies. Okay, that's different from formation enthalpies.
Yes, opposite sign convention, because bond enthalpies are usually defined as energy required to break bonds. Positive. Good catch. Next, lattice enthalpy, lattice HR. Crucial for ionic compounds. Lattice enthalpy is the enthalpy change when 1 mole of an ionic compound solid dissociates into its constituent gaseous ions. Example, NaClS, NiO plus Clubri, lattice H plus 798 kJ-mol. Always positive, needs energy to break the lattice. It's impossible to measure directly. So we use the Born-Haber cycle. The Born-Haber cycle uses Hess's law. It's a cycle of steps where the total enthalpy change is 0, allowing calculation of the unknown lattice enthalpy. Steps for NaCl, 1 NS, NSOG plus E sub hasher plus 108.4, NaRG plus Ia, ionization I at plus 496. 3. Hessology, dissociation, hapon H plus 121. 4. CLG plus E of S, E out, electron gain, AS SOS, formation from ions and elastrogy. The overall reaction connecting these is NERS plus COLA SOS, formation from ions, alidosage. The overall reaction connecting these is NOWS plus HASC, AFLS is Eckler-Nettish 411.2 kJ-mol. Applying Hess's law. SH, a Saipobat step 1 plus step 2 plus step 3 plus step 4 plus step 5. Or rearranging to find lattice enthalpy, a lattice H plus SH plus step 4 plus step 1 plus 2 plus step 3 plus step 4, a lattice H must have 2 plus middle H 4 plus 496 plus 121 plus minus 348 into plus stuff 88 kJ-mol.
Wow, that's intricate but clever. using a cycle to find something you can't measure directly.
Exactly. It's a beautiful application of Hess's law. Next, enthalpy of solution, SLH. Why do things dissolve, and why do some heat up-cool down? Enthalpy of solution is the enthalpy change when 1 mole of substance dissolves in a specified amount of solvent. At infinite dilution, solute interactions are negligible. Dissolving ionic compounds involves 2 energy steps. 1, breaking the lattice. Requires energy lattice H is positive. 2, solvating ions, surrounding by solvent, releases energy, hydration, enthalpy, but heat held negative. Overall, SO lattice H plus A held H, 8L, example, NaCl dissolution. A lattice H plus 785 NeCal. Acyl H plus 788.4 plus 984 plus 4 kilodaniolone. Small positive value, slight cooling effect, hardly noticeable temperature change.
So acyl H is the sum of breaking the lattice and hydrating the ions. Okay. My textbook mentions fluorides are often less soluble than chlorides. Why would that be? Related to this.
Fantastic question. Yes, absolutely related and common in exams. Typically, fluorides, like NaF, are less soluble than chlorides, NaCl, because the lattice enthalpy of fluorides is significantly higher. Why higher? The fluoride ion, F, is much smaller than chloride, Salor. Smaller ions pack tighter, stronger attractions, harder to break the lattice. While fluoride's hydration enthalpy might also be more negative, more energy released, the increase in lattice energy often dominates. This makes the overall acyl aeration of fluorides more positive, more endothermic, making dissolution less favorable. So yes, it's the balance between lattice and hydration enthalpies.
The high lattice energy of fluorides makes them harder to dissolve.
Got it. Precisely. Finally, briefly, enthalpy of dilution. This is the heat change when you add more solvent to an already existing solution. It depends on initial concentration and amount of solvent added. Example, dissolving HCl gas in water, HClG plus 10AQ. HCl 10AQ, HAH equals negative 69.01 kilojmol concentrated. HClG plus 25AQ, HCl 25AQ, HCH equals 72.03 kilojmol, more dilute. To find enthalpy of diluting the first solution to the second, use Hess's law. Subtract EQ1 from EQ2. HCl.10AQ plus 15AQ plus 15AQ, HCl.25AQ, HEH net is 72.03, circulation 301, gives me 99.01 EQ line, it equals 6002 kilojmol. Heat is released when this HCl solution is diluted further. Interactions change. Okay, we've covered a lot about energy changes, AAAAAH, but the first law doesn't tell us if a reaction will actually happen on its own. This brings us to spontaneity. What is spontaneity? In thermodynamics, a spontaneous process has the potential to proceed without the assistance of external agency. Think, a ball rolls downhill, gas expands, iron rusts. These happen on their own. Important. Spontaneous just means it can happen, not how quickly. Exactly. And a spontaneous process is irreversible. It won't reverse on its own. You need external work. This leads to a hypothesis. Is a decrease in enthalpy, aleogeothermic, the criterion for spontaneity? Seems logical, like things falling to lower energy. Many spontaneous reactions are exothermic, combustion, NHA formation. However, this is not universally true. Many spontaneous reactions are endothermic, AOG, examples. AAG plus OG, AOAG plus 33.2 kilojmol forms in smog. C graphite LiSO plus 2SO AJOs plus 128.5 kilojrel. These absorb heat but still happen spontaneously.
So being exothermic helps, but isn't required for spontaneity.
Precisely. Decrease in enthalpy is a contributory factor, but not the sole criterion. There must be another driving force. So what else drives spontaneous processes, especially endothermic ones or those with AH arrow? This brings us to entropy. Think about mixing two gases. No heat change, NHA 0, but they mix spontaneously. Why? Before mixing, molecules are ordered, gas A left, gas B right. After mixing, it's random, less predictable, more disordered.
More mixed up, more chaotic.
Exactly. There's a natural tendency for... Now, how to quantify US? Crucially, like U and H, entropy S is a state function. US is path independent. Heat Q adds randomness, increases motion. EOS is proportional to Q. Adding heat at lower T causes greater relative randomness than at higher T. So US is inversely proportional to T. For a reversible process, US equals CREV T, equation 5.18. This is how we calculate it. Now, for spontaneity, it's the total entropy change of the universe that matters. Total E system plus or surrounding 0 for a spontaneous process, equation 5.19. This is the second law of thermodynamics. At equilibrium, entropy is maximum, and E total equals 0. Unlike U, E total does discriminate. Reversible, irreversible, spontaneous, EO equals Xable.
So total entropy increase drives spontaneity.
Let's use this to predict entropy changes qualitatively. Problem 5.0. Predict entropy increases and decreases.
How a liquid crystallizes into a solid. Order, freedom.
Liquid to solid. Molecules get fixed in a lattice, more ordered, less freedom, entropy decreases.
Correct. Part 2. Temperature of a crystalline solid raised from 0K to 115K motion. At 0K, almost static. As T rises, particles vibrate more. More motion, more disorder. Entropy increases.
Precisely. Part 3. Nost K0 plus HOG phase.
One solid reactant. Products are a solid plus two gases. Gases have much higher entropy, so entropy increases significantly.
Excellent observation. Gas formation usually means Euros increases. Part 4. H. Euler's number of particles.
One molecule breaks into two atoms. Number of particles increases. More particles, more disorder. Entropy increases.
Absolutely right. These qualitative predictions are often asked. Now, a very important conceptual problem. Problem 5.11. Oxidation of iron. 4 Se plus 3 others 2 Euros. Air Sonichus Anekij 500-648 SAS 10 Memory G Y spontaneous air MX time to 1949 pies 2 ananas. System entropy decreases, yet rusting is spontaneous. Why? Remember, spontaneity depends on total air system plus S surroundings. How do we find air surroundings?
Use the formula.
Yeah.
Shear C surroundings is 10 Mary. The minus sign is key.
Precisely. Plug in values. Air area Anekij 648 times 198 annex. Air era AOE. Calculate it.
Okay, yay surroundings. Liga centin 48 thircianate. 298 Ks. 298 Cos. 248,298 effectively entered 530.2 JHA covertly. Positive large value.
Excellent. Now calculate Sadal system plus lay surroundings.
Its total leg is 549.4 J-comolu plus 555.30.2 J-comolu is a 490.8 J-comolu.
And is this positive or negative? What does that mean?
It's positive. Since total zero, the reaction is spontaneous. Even though the system gets more ordered, the huge heat release makes the surroundings much more disordered, driving the overall process.
Precisely. A very common conceptual question. Always consider the surroundings. Since neither ISU nor AS alone is enough, we combine them into the ultimate criterion, Gibbs energy, G, or free energy definition. G equals HTS, equation 5.20. G is extensive and crucially a state function. G depends only on initial and final states, change in Gibbs energy at constant T. HE, equation 5.21. The Gibbs equation, vital for chemistry. Units are energy, J or kJ. Now, relationship to spontaneity, recall. The total is just a system. For spontaneous process, the total is 0. So BJ system 0, 0, or E is system 0, rearranged at E system 0. Since AG is chase, this means NISU 0 or AG 0, equation 5.22.
So AG0 is the criterion for spontaneity at constant T and P.
Exactly. The definitive criterion. E, 0, negative. Spontaneous. AG, 0, positive. Non-spontaneous. Reverse is spontaneous. AG is spontaneous. Equilibrium. AG is often called free energy because it represents the maximum useful non-expansion work obtainable. Now, let's summarize effective temperature on spontaneity using Eddige-Telfak science, table 5.4. Case 1, AG plus, 2 plus, always negative, spontaneous at all T, both factors favorable. Case 2, plus, TG becomes plus T plus, negative spontaneous only if negative ides dominates positive edges. Spontaneous at low T, enthalpy driven. Case 3, Edge plus, TD plus, TD plus, negative spontaneous only if positive T dominates positive AG. Spontaneous at high T, entropy driven. Case 4, AG plus, case T becomes plus T plus, always positive, non-spontaneous at all T, both factors unfavorable.
And that table is really ususeful for predictions. Depends on the signs of the temperature.
Absolutely. Low and high T are relative. This analysis is key. Let's briefly summarize entropy and the second law. First law, energy conserved for isolated system.
For spontaneous change in an isolated system, entropy S increases. Nature tends towards disorder.
This explains why exothermic reactions are common. Heat released increases surroundings entropy, making total positive. And finally, absolute entropy and the third law. Molecular motions, translation, rotation, vibration, contribute to entropy. Higher T, more motion, higher S. Third law, entropy of a pure crystalline substance approaches 0 as T approaches absolute 0, 0K. Reason. Perfect crystal at 0K has perfect order, minimum motion, S0 importance. Allows calculation of absolute entropy values from thermal data, needed for calculating entropries.
Third law gives us a 0 point for entropy.
Exactly. Now let's connect Gibbs energy to equilibrium. For a reversible reaction at equilibrium, A plus B, D plus D, Gibbs energy is at its minimum, no tendency to change. At equilibrium, error G equals 0. This is the thermodynamic definition of equilibrium. Now the crucial link. Relationship between standard Gibbs energy change and equilibrium constant. A must-know formula when all substances are in standard states. Error equals RT-ln-K, equation 5.23. Or using log base 10, error G equals 2.33 RT log K.
Error not equals minus RT-ln-K. Very important.
Extremely. Implications. Large positive area carrier K1 reactants favored. Large negative error J area K. Products favored near completion. Error seg also affects K via error area. Practical use. Calculate K from area estimated from area AS, or vice versa. Let's apply it. Problem 5.1 to be calculate area at 298K if Kp equals 2.47, all 10 or 1. Use area J equals a net of 303 RT, R 8.314 JL, T equals 2.47, R 10.
Okay, log 2.47228 is roughly negative 28.60.
Excellent. Now plug all values into the formula. Calculate area G.
G, and it is 2.303, 8.314, 298, and it is 28.60. Pause. Comes out to about 163,309 DJ molar, or 163.4 kiloJ mole.
Very good. Large positive Erg. What does this indicate?
Highly non-spontaneous. Makes sense. Ozone doesn't just form from oxygen easily.
Precisely. Now the reverse, problem 5.13. Find K for a reaction at 298 K if Erg is 0.60.6 kiloj mole. Rearrange. Log K Erg is 2.303 R key. Careful with units. Ager and KJ, R and J convert R to KJR, 0.08314 kiloj mole.
Okay, log K already the 13.6 kilomole, 2.303 is 0.08314 kJ kmol, 2.4, 2.708, 2.38.
Now find K from log K.
K equals 2.384. Pause K at 2.4 times the pan.
Great. Shows how thermodynamic data predicts reaction extent. Finally, problem 5.14, typical JEE level. At 60 degrees C, NO is 50% dissociated. Mole is at equilibrium. Total moles start 1 NO, 50% dissociates, 0.5 mole. NO remaining, over 1.5 NO formed equals 3.5 per 1 mole. Total moles equals 1.5 plus 1 plus 1 plus 1 plus 1 plus 1.5 mole. Perfect. Now partial pressures, mole fraction, total pressure, 1 atm.
Mole fraction N euro 0.5 equals 13. P N euro 13 at N euro. Mole fraction N euro 11.5 equals 23. P N euro 23 at the end.
Excellent. Now KP expression and value.
KP P N euro 13 euro 33 equals 43 equal 1.3338 here.
Fantastic. Final step. Calculate area G using area of G and area D and KPT 60 degrees C equal 333K. RE is 8.314 J kmol.
Okay, LN 1.333. Area D only knows 8.314. J kmol 333K 0.287. Pause gives about a negative 797 J mole or does that get 0.797 kmoles a molar.
Process is perfect. Slight rounding differences are okay. Small negative euro, what does it mean?
Negative euro means dissociation is spontaneous at 60 degrees.
Exactly. A brilliant problem combining equilibrium and thermodynamics. Well, we've truly covered a vast and crucial landscape today. From basic definitions, the first law, enthalpy, Hess's law, all the way to entropy, spontaneity, Gibbs energy, and its link to equilibrium.
It's so much clearer now how all these concepts, the first law, Hess's law, Gibbs equation, tie together. The problem-solving examples really helped connect the theory to practical application for exams.
Yeah.
Made it much less abstract.
That's exactly what we aimed for. Remember, thermodynamics isn't just about memorizing formulas. It's about understanding the deep principles of energy and spontaneity governing everything around us. For your upcoming Class 11th boards, and especially for JEE and NEET, revise these concepts thoroughly. Practice past year questions based on these derivations and problem types. And most importantly, always feel free to reach out if you have more doubts on this vital chapter. Keep practicing, keep learning, and best of luck with your studies.